All right, Archimedes Principle. We're talking about fluid statics here. These are fluids that aren't moving. When we talk about moving fluids, we're going to talk about a principle known as Bernoulli's principle. That's different. We're going to keep getting stationary. All right, floating. Very, very simple term, but you got to understand what floating means in physics. When something floats, that means that there's an upward force which counteracts its own weight. And when you float, that upward force is equal to the weight. It's like a frictional force. It's less than or equal to, but it can never be greater than. If you're floating in water, you can't have a force upwards that's greater than your weight. Otherwise, you accelerate out of the water. It doesn't make any sense. So it's kind of similar to normal force, too. If I put something on a table, the normal force pushes up only as much as it needs to in order to get the object to float or sit on the table. We're going to identify this upward force as buoyant force. And when we draw free body diagrams, it is going to be, or I will use F sub B for buoyant force to designate buoyant force. Anytime an object is touching a fluid, it experiences a buoyant force. You are experiencing a buoyant force right now. You are buoyant in the atmosphere. So technically, when you get on the scale, you weigh slightly less than you would if you were on a scale without any air in a vacuum. Now, the buoyant force due to air is almost nothing because the density of air is very, very low. Buoyant force goes up as the density increases. If you were to get in a pool, you would experience a great deal of buoyant force. Not because you're displacing more water, but because the fluid that you're in has a high density. If you were able to get into, say, a vat of oil, you would experience even more buoyant force. The higher density stuff that you're in, the more buoyant force that you experience. Archimedes Principle, and this is the crux of the principle. A body immersed in a fluid is buoyed by a force equal to the weight of the fluid it displaces. The weight of the fluid that is displaced. So it depends on the density of the fluid, local gravity, and the volume of the fluid which is displaced. Mathematically, we'll get there. Mathematically, rho Vg. Buoyant force is rho, the density of the displaced liquid. It's got to be the liquid. Almost always in problems dealing with density, or dealing with buoyancy, they give you the density of the fluid and the density of the object. You have to keep those things separate. Fluid density. The volume of the displaced fluid. Now this is a little bit tricky too, because we care about the volume of the fluid that's displaced, but that is almost always equal to the volume of the stuff, the object you put in the fluid. Now when is it not equal to the volume of the object that you put in the fluid? When it floats, right? When only half the object is underwater or 3/4 of it's underwater. Then the volume of the object and the volume of the fluid won't be equal to. If the object has sunk in the fluid, the volume of the object is equal to the volume displaced. When the object floats, the upward buoyant force equals the downward force of gravity. So a free body diagram of a floating object would look like this. You have a downward force due to the weight of the object and an upward force due to the buoyant force. When an object is floating, the sum of the forces is 0. So the buoyant force equals the weight of the object. And once again, buoyant force is kind of like normal force. It doesn't have to supply all that it can, just enough to support the object. As long as you displace enough fluid, you can float nearly anything. Aircraft carriers are a great example of that. Things are made of solid steel. You put a piece of steel in water, it's going to sink. How do these things float? they displace enough fluid in order to float. That is the only thing that experiences a buoyant force. So they do the calculations and say, how much do I have to have underwater in order to keep my ship afloat? Yes, Sam? Do boats create lower virtual densities? No, density is an inherent property of matter. So yeah, I don't know if I would call it virtual density. It has an apparent weight loss. I guess that's more terminology that we would use in physics. If you are in air, you may weigh 500 newtons. I'm not sure I follow exactly what you're going for. When you put something in a fluid, it does have an apparent weight loss, but you can't say that its density changes at all. Because the density is its density regardless of where or what it's in. Yeah. Submarines, for those who are going, I guess this is kind of the same way. Submarines, for those who are going into that field, use water to vary their own density so that they sink or float. They take on water to increase the density so that they sink, and then they purge the water in order to decrease the density so that they float. And they can raise or lower their position in the water based on how much water they input or output. So let's just take a minute to solve a hypothetical question. Let's say we've got a box and we put it in some water, and 75% of the volume is now above the water. So we've got a fluid and we've got a box that's in the fluid, and 75% of the volume of this object is under the water surface. And what's the density of the box? There's a relationship between how much sinks and what the density is. And that's what we're trying to show here. Well, Archimedes' principle states that the buoyant force is equal to the weight of the object when it's floating. And we went through that derivation just a minute ago. Well, the buoyant force due to the water is the density of the fluid, the volume of the fluid displaced, and gravity, or VG. Mass of the box, well, we don't know what the mass of the box is. We want to know what the density of the box is. So we take a little aside here and say the density of the box equals the mass of the box over the volume of the box. So the density of the box times the volume of the box equals the mass of the box. We take that. Density of the box, volume of the box, times gravity. The volume displaced, the density of fluid, the volume displaced is 75% of the volume of the box. 0.75 volume of the box times gravity equals density of the box, volume of the box, times gravity. Box, gravity. So we're left with the density of the box is 75% of the density of the fluid. So that's the relationship. Whatever percentage the density is, that is the percentage which sinks. So if I have a box that's 50% the density of the water, 50% of it will be underwater. If I have a box that's 10% of the density of water, only 10% will be underwater. If I have a box that's 100% the density of water, how much will be underwater? 100% of it. If I have a box that's 150% the density of water, how much will be underwater? Don't say 150%. 100% of it. The whole thing is going to sink. So this tells us that when something is more dense than the fluid, it sinks in the fluid. 100% you can actually, yes, it will be completely underwater, but you could float it wherever you wanted in the fluid. If I had a container filled with a fluid and I had an object which is the same density, I could put it right in the middle of that, and it would stay right in the middle of that. It could be anywhere in the fluid as long as it was 100% underwater. So whatever the density of the box is, that's how much is underwater. So if you see an object or if you have a problem where you can calculate the percentage that's underwater, you can automatically find the density of both things. That is very, very helpful. So just to sum up those 2 points. It floats only if the density is less. And however much is under the water is used to determine its density. You have to remember these 2 things. The problems will force you to use those. Any questions about floating and density?